This is a review for Chapter 19, Thermodynamics. There are a couple key equations that we've learned in this class, and the repeating equation that we keep seeing over and over and over again is this idea that if we're dealing with the functions in If we're dealing with the functions in their standard states, we can just say that the delta G, the delta S, or the delta H are just the products minus the reactants. And of course, we know that we have to multiply each of those by the coefficients if there are any. In this first example here, we do not have any coefficients, so everything is just going to be multiplied by 1, or in other words, we do nothing. So here we want to know what is the delta S of this reaction right here. Okay, so this is example 1. This is a very, very straightforward problem. What we'll be given is an equation, and then we'll be given some data similar to those numbers on page 1059 in your book. So in this case, I can just tell you, since I don't have the actual chart up here, these are the numbers associated with each one of these molecules. Okay, and of course, these are all in joules per Kelvin, generally mole. Okay, so these are joules, not kilojoules. That's going to be important later on. So what we want to do is we want to get the delta S for the products minus the delta S for the reactants. So we're going to set it up with the products first, minus, and then the sum of the reactants. Okay, and when we do the math, we get, just pull this one down, we're going to get 331.38. And when we do the math here, we're going to get a negative 111.98. Or, of course, we could say negative 112, and that will be in joules per Kelvin. Okay, and we can kind of double check this. Here we have a negative entropy, and that makes sense because if we look back to our equation, we're going from 2 moles of gas to 1 mole of gas. So we know that entropy is decreasing. So we can say that this reaction is non-spontaneous. It's non-spon because entropy is decreasing, and we know this. We also know it's non-spontaneous because we have a negative sign there. And in order for a reaction to be spontaneous, the delta S needs to have a positive value. Okay, let's do another example. This is example 2. All right. I wasn't able to get the actual problem on here, but I can kind of give you the gist of what they're saying. They're saying, what is the delta G of a particular reaction? And they'll give you a reaction. It's not very relevant, so I have not copied it down here. But what is the delta G at, and then they'll give you a certain temperature, and generally they're going to try to trick you and give you the temperature in Celsius. So in this particular problem, we want to know what is the delta G of a particular reaction, again, which I have not written, at 100 degrees Celsius. So then they're going to give you some other information. We're given the delta H is negative 795 0.8, and of course that we know is in kilojoules per mole. And then we're also given the entropy, which is negative 159.8, and we know that that's going to be joules per mole, which can be kind of a problem. Now, the main equation that we're going to want to use is our delta G equals delta H minus temperature times delta S. Okay, that's our main equation. Now, we know that temperature has to be given in Kelvin for this equation, and we know that this is going to be needed. We need to convert the entropy to kilojoules, even though we're given the problem in joules. So let's do a little bit of work here. Of course, they're going to try to make this more complicated, so our temperature we need to convert to Kelvin. So what we do, we just are going to add 273, and that's going to give us, of course, 373 degrees Kelvin. Let's just move this up. Okay. So we have 373 degrees Kelvin. So we've got our T, and then our delta S needs to be converted to kilojoules. So we're going to move the decimal 1, 2, 3 spaces to the left, and we can rewrite that over here as a negative 0.1598, and that will be kilojoules per mole. So now we're ready to plug it into our equation. We're solving for delta G, so we're going to say delta G equals negative 795.8 for our delta H, and then minus, we have our new temperature at 373 degrees Kelvin, and then our delta S, which will be negative 0.1598. Now when you're using this equation here, you want to kind of just be checking your work. Your delta S should generally be a very small number. If it's not, you know that you forgot to convert it from joules to kilojoules. So when we just go ahead and solve this, we have negative 795.8, and it's going to be plus 59.61 because we have a negative 373 times a negative 0.1598, so we know that we're going to get a positive number, and that's equal to delta G. And our final answer is going to end up being delta G equals negative 736.2, and that will be in kilojoules per mole. Okay, and that's our final answer. All right, let's do another example. Go away. There you go. Okay, so this is example 3. All right. In this question, we also want to use this same equation where we have our delta G equals delta H minus T delta S. Okay, we're still going to use that equation. And this one's a little bit trickier. What they're asking is they want to know, all right, given a specific reaction, we're going to give you some information. We're going to give you a delta H and a delta S. And the question's going to say, at what temperature is this reaction going to be spontaneous? Okay, the exact question says, at temperatures greater than blank degrees Celsius, is the reaction going to be spontaneous? So, once again, the reaction isn't actually important in this. They're going to give you a whole lot of information that you don't need. But they do give you some information. They give you a delta H is equal to 131.3, of course, kilojoules. And we're given a delta S, which is 127.6 joules per mole. Right away, we know that we're going to have to convert our delta S, so I'm just going to do that right at the beginning. So 1, 2, 3, can rewrite this 0.1276 kilojoules per mole. Now what we know is that when delta G is negative, the reaction will be spontaneous. When delta G is positive, the reaction will not be spontaneous. So in this case, what we can say is we can set delta G equal to 0 so that we can say what is the threshold value for temperature that is going to make delta G negative. Okay, so whatever temperature we find, we know that any temperature that's going to be greater than that will make this this reaction run spontaneously. Okay, so we're going to use our equation, but this time we're going to put 0 in for G, and then our delta H, which is 131.3, and then minus, we're going to solve for T, right, because the question's asking what temperature, and then we're going to plug in our S, and we're going to do that quick check, make sure our delta S is very small, and it is, so we're ready to go. So first move is I would do minus 131.3 from each side. So we're going to get a negative 131.3. It's going to be equal to a negative T times our delta S. Okay, I can divide each side. And I end up getting T is equal to approximately 1028. Now, this is really important because we need to keep in mind that our T, when we're using this equation, is going to be in Kelvin. They ask, what temperature in Celsius is this reaction going to be spontaneous? So we need to take this and we need to subtract 273 to get back to Celsius. When we do that, we're going to get 756 degrees Celsius. And that is our answer. Okay, I'm going to have to post an additional video so that we can go over kind of a last final example that's a little bit complicated. So stay posted and there'll be a second video.